Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be studying how the different control inputs going to be affected on the attitude convergence of the aircraft. We'll find the relationship between the attitude of the aircraft with respect to the reference signal, attitude of the aircraft with respect to disturbance as well as the noise. Then we'll see the combined effect of these control inputs on the attitude convergence of the aircraft. And also we'll be studying how the controller going to be placed an important role for mitigating this disturbance, which is basically unfavorable disturbance to the system. Then we'll conclude the lecture. We'll continue from the last lecture. In the last lecture, we had the closed loop feedback controls for the aircraft attitude systems. Let me read out the figure again, then we'll proceed. So we had our controller transfer function GC of S, and the output from the controller we had U of S, and we had summing point, and in the summing point there is two input. One is MDS, which is the disturbance, and the summed output from this block was going to the plant, which is GP of S, and the output from the plant was Y of S. And we had another summing point. We are having the reference input RS. This is, we can say YDS, or we can say theta DS. And we had another input to this summing point. So we had noise in the system WS. This is negative feedback. And the sensor transfer function, we assume H of S equal to 1. This is basically unit feedback system. And this is the input to the sensor transfer function. And the error was going to the controller. This is E of S. Now, in this lecture, we'll be finding the transfer function Y of S with respect to disturbance MDS, Y of S with respect to R of S, the reference signal, Y of S with respect to W of S. So how the different transfer function we can derive. So let's start. So since we are handling the CISO system and transfer function, generally we come up with for the CISO single input and single output system. So we can't take all the inputs at the same time. We have to take one at a time. So let YR be the response to the reference signal with MDS equal to 0 and WS equal to 0. So first we'll find the transfer function YS with respect to RS, which is when we are having YS with respect to RS, I am denoting YSB RS, YRS. and we are assuming the other input signal assumed to be 0. And in this situation, our closed loop transfer function can be drawn as, this is the summing point, where we are having RS as a reference signal, and here we have controller block GC of S, and since we are not assuming the disturbance, the input is going to the controller. This is my U of S, this is the GP of S, and the output for this case I am assuming Y RS. And also we are assuming there is no noise. This is my negative feedback, this is positive. So this is how, in this condition, this is how we can draw the block diagram. Let me draw this figure number 1. This is figure 2. Now let's find the transfer function YRS with respect to RS. From figure 2, we can write YRS, we can have YRS equal to, okay, here let's denote this is my E of S. So it will be multiplied GP into GC into ES. So GPS, GCS, and ES we can write. And also we have ES equal to, we can write RS minus YRS. So that we can write YRS equal to, we can write GPS, GCS, in place of ES we can write this expression RS minus YRS. This you can write, and if you multiply, we'll have GP of S, GC of S, RS minus GP of S, GC of S, YRS. And after rearranging the equations, we can write YRS plus GP of S, GC of S, YRS equal to GP of S, GC of S, RS. Further we can write, we can take YRS common from the left hand side, YRS 1 plus GP of S, GC of S equal to GP of S, GC of S, and RS. And from this we can write YRS divided by RS equal to GP of S, GC of S divided by 1 plus GP of S, GC of S. So this is basically the closed loop transfer function, which yields the relation between YRS and RS. This is basically the main transfer function, because in this transfer function, how we're going to track RS. So let's denote this equation number. This is equation number 1. So first transfer function we have found. Now we will go to the second transfer function, which is with respect to disturbance, the effect of disturbance on output. So now let YDS be the response to the disturbance MDS with, so we have to consider one input at a time. So other input will assume to be 0 with RS equal to 0 and WS equal to 0. And in this situation, let's draw the figure, the closed loop diagram. This is our summing point, and this is RS, which is equal to 0, we assumed, and controller block will be there. This is GC of S, and in this case, we will assume disturbance, which is MDS, and this is US, and the sum output going to the plant, which is GP of S, and the output we are denoting here YDS, and also we are assuming unity feedback with WS equal to 0. So this is the closed loop transfer function when MDS only acting, other inputs are assumed to be 0. And let's denote this figure number 3. From figure 3, we can write YDS equal to GP of S into MD of S plus GC of S, E of S. So again, you can write E of S here, E of S, you can write. And if you multiply the factors, GP of S, MDS plus GP of S, GC of S, ES. If you notice here basically E of S, we can write minus YDS because RS is assumed to be 0 here, because ES, actually we know ES R of S minus YDS. So here RS is 0, so it's only YDS. Now if we substitute this expression in this equation, we'll get YD of S equal to GP of S MDS minus GP of S GC of S YD of S. After rearranging the equation, we can write YDS plus GP of S, GP of S, GC of S, YDS equal to GP of S, MD of S. And from this expression, we can take YDS common, 1 plus GP of S, CC of S equal to GP of S, MDS. And further we can write YDS by MDS as input, reference input, not reference, disturbance input, and GP of S 1 plus GP of S, GC of S. So this is the second equation which relates between the disturbance and output signal. So how the disturbance is going to affect on the output? I mean, output means the attitude of the aircraft. How it's going to affect? This is the relation. Now we'll get the final transfer function with the effect of noise omega s. So let YWS be the response with the measurement noise WS. So here we'll assume RS to be 0 and MDS to be 0. So in this condition, let's draw the figure, how the figure will be look like. So this is our summing point. This is the reference signal, which is R of S, which is assumed to be 0. And this is the error signal we are producing. So this is ER S, and the control is GC of S, and here we can have a summing point here. So here MDS equal to 0, we have already assumed, and this response is going to controller, which is GP of S, and the output from this we are denoting WS. And here we are assuming there is a summing point, and where WS is acting, and this is my feedback loop. This is plus, this is plus, and this is a negative feedback. And from this figure, we can write from figure, this is, let me figure number 4. From figure 4, we can write YWS equal to GP of S, GC of S into ES. But here actually, since we are assuming measurement noise in the system, and we can write E of S, we can write R of S minus YWS plus WS. But here we already assume that R is to be 0. So we can write the error is basically minus YWS plus WS. Now, substituting this expression in this equation, if we substitute this expression in the previous equation, we can get equal to, we can write minus GPS, GCS, YWS plus WS. And from this we can write YWS equal to minus CPS, GCS, YWS minus GP of S, GC of S, WS. If you rewrite the equation, rearrange the equation, we can write YWS plus GP of S, GC of S, YWS equal to minus GP of S, GC of S, WS. If you take YWS common from the left hand side, we can write 1 plus GP of S, GC of S equal to minus GP of S, GC of S, WS. we can write further YWS divided by WS equal to minus GP of S GC of S divided by 1 plus GP of S GC of S. So this is the transfer function which relates between the output and measurement noise in the system. So this is, let me define this equation number 3. If you notice very carefully, in this 3 transfer function, the denominator part in all equation are same. If you see the first equation, this is our denominator part. The second equation is the denominator. The third equation also is denominator. So denominator part is remain to be same. Now this is very, very important observation. How we can see the system with the different inputs, disturbance, noise, reference signal. Okay, now since the system is linear, we can combine the effect. So let's write the combined response to RS, MDS, and WS is the sum. So we can write, let's assume YS is the total response. We can write YRS plus YDS plus YWS. And we can further write, so YRS basically we can write YRS equal to this whole transfer function into RS. Similarly, YDS we can write the whole transfer function with MDS. Similarly, the YWS equal to, we can write the whole transfer function into WS. So we can, let me write GP of S, GC of S divided by 1 plus GP of S, GC of S into RS plus GP of S 1 plus GP of S, GC of S into MDS, and minus GP of S, GC of S divided by 1 plus GP of S and GC of S into WS. And let's write this equation number 4. So in this equation, many things we are going to observe. This is very, very important equations. Our main motivation is, if you see the control objective, our control objective is YRS matches with RS. This is our main objective, or we can say matches with theta. This is theta S should matches with theta desired, or Y of t should matches with Y desired t. This is our main motivation, because R is basically desired signal or reference signal, the system. So this is the main motivation in control system, how we can come up with our desired signal with the application of control. But if you look in this, in equation 4, in the equation 4, if you notice carefully, GP of S is the plant. In the plant, we can't do anything. plant is coming from the natural motion of the system, natural dynamics. So plant is coming from the natural dynamics. So we can't play anything on this transfer function. This is the basically the main plant transfer function. So we can't do anything here. And the other transfer function, GC of S, is the controller. So controller, basically, it can be artificial device or some human being. Some kind of mathematical formulation we are doing here, which is basically the control engineers does it. So here we can say this is up to the control engineer. So we can modify it, we can change that to the defined control algorithms. It is up to us. So now, if we can design some control algorithm, if we can design some control algorithm where GC of S magnitude is very large, because in control, basically, there are a lot of gains will be there. We'll be talking later, but let's assume the control algorithm we designed is very big. Let me write. Let the control be large. So in this case, if GC of S and GP of S is the magnitude of this value is bigger than 1, then what you get? Then we can say the first term in equation 4, this is going to be 1, because this term is bigger than 1, this term. Then both will be cancelled out. One you can ignore here. So this term and this term will cancel out. So we can say in this situation, in this condition, we get YRS goes to YS. But there's a problem. Okay, let's not to go to the problem again now. So now, if it is very large, again, let's go to the second term. Then we can, if it is very large, GC of S compared to GP of S, so this term we can say goes to 0. So it means even the disturbance is there in the system, YS can track RS, because with this assumption, the disturbance acting on the system can be neglected in this condition. This is very, very important takeaway from this discussion. So first, if you can design our control, algorithm, this control algorithm, in such a way that this condition will fulfilled, and then we can get, let me write here, we can get, from this discussion we can write GP of S, GC of S divided by 1 plus GP of S, GC of S is equals to 1, and GP of S 1 plus GP of S, GC of S goes to 0. So this is very, good thing that if you design control in such a way that both this condition can be satisfied, so we can get perfect tracking. But in this condition, there's one problem. In this condition, with this condition, there's a problem on the noise. So with this condition, we can write with the above condition, YWS is going to be minus WS, because if you look this equation, this equation going to be 1. What you have done here, if you notice here, this is what we have done. So this, with this condition, this is the case, this is the problem. So if this is arises, we can't get perfect tracking because WS also in this equation. So this is the compromise we face as a control system engineer. So this problem can be tackled if you come up with some frequency analysis like Nyquist or Bode plot. Those things we'll be talking later. So because noise are basically high frequency signals. So this thing we can tackle while we'll be designing the control algorithm based on in the frequency domain. So that with using that concept, we can tackle this part as well. But this is the main motivation that in this lecture, that this is what you have done here. This is, if you can do, at least we can get our tracking. But this can be done with the help of some navigation algorithms or some frequency analysis design based control. We can tackle this problem as well. And this is the main motivation of designing control algorithms, so that we can get our tracking algorithm. So, and we can tracking algorithm means we can get our desired attitude angles with the help of control algorithm, which should be designed very carefully so that we can get this kind of objectives. Let's stop it here. We'll continue from the next lecture. So next lecture we'll be discussing how we can come up with some typical control algorithms and how we can get our desired response in the closed loop control system. And we'll be designing all this algorithm for the aircraft autopilot design, how we can control the orientation of the body of the aircraft. Let's stop it here. We'll continue for the next lecture. Thank you very much.